Okay, awesome. Thank you, Ted. Sorry I can't be there in person this week. I'm in Seattle for the weekend, so I'll be back in the future sessions. But for today, I'm away, so we'll have to do it remote. Thanks, Liam and Ted, for organizing everything in person. Thanks everyone for showing up. So, last week we had chapter 8 that Liam covered, getting us into sort of the real ML after the math kind of precursor. So now we're moving into the first section, sort of some basic building blocks. So linear regression is very important. It's the foundation of a lot of the stuff that builds in the future. So all of the neural nets and that stuff is kind of extensions of linear regression if you think about it. So um, linear regression is still popular, but I think the bigger thing is understanding what it can build into in the future. That's kind of the hot thing in the future. Um, so just talking a little bit about our objective here, what we're really trying to do is we're trying to find a function that doesn't only model the training data. We're also trying to find something that generalizes to new inputs. And so linear regression is a great tool for doing that. So a linear model, ultimately what it's doing is it's trying to fit a line to some inputs and outputs. So like we have here in the graph below, you have this sort of curve that's represented by a bunch of measurements. So they took some data and they said, here's some X's, here's some Y's, and try and fit a line to this basically. Um, and so I typically think of it as like the y equals mx plus b that we learned early on, but kind of this alternative way of thinking of it is that we're trying to find at each individual point. So like imagine here at -4, you could measure many samples of that. So say you had 1,000 samples just at -4. You're going to have some that are a little bit higher, some that are a little bit lower. So it could just be measurement noise, it could be messiness of the real world, it could be any number of different things, but you're going to have sort of a distribution even at just -4. So this is kind of what this little yellow squiggle is representing, saying like this is the most likely outcome, but it could be higher, could be lower, just based on noise. Um, so when we're looking at this kind of modeling, there's a few different things that we can look at. So like the model type and the parameterization. So we can do polynomials and we can choose what degree they're set to, and there's a bunch of different decisions that can be made there. And then the other piece is finding the optimal parameters. So once we've defined what are the parameters of our, or what are what is kind of the shape and type of our model, then we have to figure out how do we find the optimal parameters to put inside of those models. So does this weight be -3 or 7 or something else? Um, and so there's different processes for how we measure how good a perimeter is, and then there's also choice of how we actually optimize those. Um, and then the next section is talking about overfitting. So you want your model, in theory, to typically not just represent your training data as well as possible, the data that you've measured before. You want it to also work well on new inputs. So if you said, I've taken 100 data points, but now I want to kind of interpolate between those and understand um, if you have values at 2 and 3, you want to know what's at 2.5, for example. Um, and so you need something that is capable of handling that task of figuring out stuff that you haven't measured before. So there's a relationship between the loss functions and the priors. So if you have some idea about what the parameters should look like, that can also inform the loss function that you use and vice versa. And so another one of the valuable things with linear modeling is with the Bayesian side that we'll see later. Um, you have some form of uncertainty modeling, so you know how uncertain the model is at various different regions. So if a model is very certain in some certain band of values, then you might say, okay, I'll use this model now. But if you say extrapolating to some higher value, it has very high uncertainty. I don't know if I should trust this model as much. So that the Bayesian linear modeling is also very useful for that. Um, so digging into the sort of problem formulation for linear modeling, ultimately what we're trying to do is we're trying to find some parameters data that work well for our data. So we'll look at what work well means in more detail later, but for now, just basically say um, so we have some parameter theta, and that changes the slope of our line. So this plot on the left is showing we have a whole range of potential lines that we can draw, all different slopes, and we can change this. And then we have some training set here. So here's a bunch of measurements that we've taken, so X, Y values. And then it's saying what is the line that makes the most realistic outcome. So there's some slope that says it goes through most of these, and it is the has the highest likelihood um, from the lines that we can draw, just varying that parameter. Um, So that technique, maximum likelihood estimation, ultimately what we're trying to do is find the parameters that maximize the likelihood of Y given X. So you have some variable X and you say what's the most likely outcome um, given the parameters that I found. So you want to adjust those parameters in order to make the Y a very likely one ultimately. Um, so in the vein of what I was mentioning earlier, where you want to kind of measure how well a specific set of parameters works, you can measure it with something like negative log likelihood or squared error. There's various different things that is mentioned in the book, and so this is what negative log likelihood looks like. Um, so it's the probability of yi given xi. So we have some specific input x and output y, and then we have our parameters theta. And so ultimately what we're trying to do is we're trying to make the most likely outcome with this. Um, and so we have some loss function, and then we can say compute the gradient with respect to that loss function. And then in with the right constraints, we can say compute the gradient and then set that to zero and then solve for our parameters. So it's a closed form thing where you can say just directly calculate what is the global optima value. Um, so it's much more complicated in certain other cases where you might not have linear models or the right constraints in place. But with this, it's something where you can just directly calculate and say this is the parameter that minimizes this. So um, looking back on the previous slide, um, we can say we're only optimizing one parameter here, the slope, but we can say sweep through all of these values, measure the negative log likelihood, and then we can say this one's optimal. But we could do it just by sweeping through the values, but also we can just calculate it directly, saying we know the gradient and we're able to set it to zero and solve for those parameters directly. Um, so one thing about this is when I think of linear regression, you think of here's a straight line. It's only able to represent things that are linear. So if I have any relationships that are more complicated than that, like I have some quadratic or something else, then I'm not going to be able to represent it well. I'll find a slope and then it will just be broken. It will just be very poorly fit to what I'm trying to do. But in reality, what you can do is you can still do linear regression, but you can do it on a sort of transformed space. So you could do something where you say instead of just having the feature X, X1, for example, you could have x1, x1 squared, x1 to the third, x1 to the fourth. And so now you have all of these polynomial inputs, and then you fit a linear model basically the same way, just on the transformed space. So you still are fitting a linear model just with more features, and it happens that those features are different degrees of polynomials that you're fitting for. And so even though you're doing linear regression technically, you can end up with a curve like shown on the right here. So you have this data set that seems to have some peaks and valleys that you couldn't represent just with a straight line, but you can represent it with this polynomial regression. Um, so this is very useful for you're using exactly the same technique. You just transform it to a new space, and then you can fit much more complicated data. So the downside of this is that with overfitting, you can end up in a situation where you have like a very high degree polynomial, for example, and it's able to completely accurately represent your training data, but it ends up with completely ridiculous um, super high, super low, waving all over the place predictions that don't actually generalize to new data. So what this plot is showing over here is basically the training error is going down. So every degree of the polynomial you add, you're fitting the training data better and better and better because you're giving your model more expressive capability. It can make more curves. It can do more extreme values. It can do whatever it needs to do in order to perfectly fit the training data. But once you start going to 7, 8, 10 degree polynomials, um, it's fitting insane curves that don't really make sense. It doesn't represent the underlying pattern. It just perfectly fits the data, and so your test error ends up going very high. So that's one of the things that you have to take account for is that you really don't want to be overfitting to your data. When you're doing modeling, you want to optimize for the lowest test or validation error. You're not optimizing for the lowest training error. So here's some examples. So using polynomial degree zero, you just have a flat line here, no slope or anything. At one, it's actually determining some slope. At three, you start to get a curve. Four, even more curvy. Six, even more curvy. And then nine, you see something that just oscillates wildly, completely out of frame. And so this is the pattern that we're kind of seeing out of that previous chart there, where um, at six, it's doing fine. It's maybe kind of diverging in terms of the test area, but at nine or 10, it's no longer making realistic predictions because it just can it can fit infinite number of polynomial values that would pass through this data, and so it doesn't choose a realistic and well-constrained one. Um, Next section, moving on to maximum posteriori estimation. I'm not sure if I'm saying that right. I don't know that I've ever said that word out loud. Um, so instead of just finding the most likely, now you're injecting some sort of prior. So you have some belief that the parameters are going to be in some range or behave in some way. And so the example that they gave in the book was a Gaussian prior. So if you have a Gaussian prior on a single parameter, it's going to kind of believe that the value is going to be within -2 and 2. And then from there, instead of just optimizing for the most likely, you're optimizing the posterior distribution. So you're kind of moving things around with a certain belief in mind is ultimately what's happening. Um, so it's a slight modification to that maximum likelihood negative log loss formula that we saw before. That's kind of introducing this log prior. So these are some graphs showing the difference that you would get doing the maximum likelihood and the map. Um, so you can see the MLE has a bit more expressive curves, not super pronounced at degree of 6, but at degree of 8, the map is probably following much more reasonable patterns than the MLE is. The MLE is saying just no constraints, fit this as closely as you possibly can, and the map has that prior encoded into it. So it's saying I expect my parameters to be within a certain space. So don't just oscillate them wildly. Don't be completely unconstrained, basically. Um, So in the next section, they were talking a little bit about regularization. So this is a way to kind of constrain your parameters, to constrain your weights. So one of the things that they were showing is you can define different norms and then set a lambda factor that is saying the strictness of your regularization. Um, so, depending on the norm that you define and depending on the strictness that you define, it can constrain your models in different ways. So, one example of that is like with P of one, you have what's called lasso regression, lasso regularization, and what this will do is it will try to push your model to use as few parameters as possible. So it's going to push any insignificant factors down to zero. That's ultimately what it's trying to do. But you can move that P up and down, and it will change the properties of your modeling and the regularization that's applied. Um, so that's a very important term. Um, you see that in deep learning, you see that in everything. Regularization is a very important thing, and you have to be kind of, depending on your constraints, decide how you want to regularize. Um, so in the last section, they were starting to talk about Bayesian linear regression. So this isn't something that I've had that much experience with. It just hasn't
Can you hear
really
me?
come up.
Can you hear me, Ryan?
Yeah, yeah.
Um, I was thinking about this chapter, and um, there's a couple of things that I thought might be useful to talk about in more practical terms. Uh, I don't know if here is a good point, or I can't remember if I don't think they revisit this after the Bayesian stuff, right? It just kind of all right. Well, I apologize if I'm not doing this exact right time, but so yeah, going back to section 9.2. So we see that there's this relationship, and we skipped over a lot of the formulas and the math and whatnot, but ultimately this L2 weight penalty, okay, which we see right in regular linear. Oh, sorry, my camera's on. In regular linear regression, then this is like ridge regression. But you see this, people use W atom optimizer all the time. I don't know right now. I think it might be more common than just vanilla atom to use atom W. Sorry. Um, so you can think about this as putting a prior. So in this case, they said, "Hey, we think that your parameters might be Gaussian distributed around zero, and so you can imagine within two standard deviations, there's not that much penalty. So if you're between -2 and +2, there's really not that much penalty. But once you start exceeding that, we're going to start really penalizing. Okay. So then if you had a different term here, then it would be a different prior, and my stats is not like out of this world, so I'm not going to be able to tell you. But let me just ask, like in practical terms, if instead of using the squared penalty with the weights, what if you used something much higher? I don't know, like the 10th power instead of the squared. Are you going to get the same solution? And what effect is that going to have on the answer that you get? Because you're still going to get a point answer, right? You're still you whether you're doing linear regression or you do a deep neural network and you train it, right? It's going to train to convergence and you're going to get a single answer. What's different about it if we do a much higher 10th degree penalty instead of a squared?
Or like if it's like dense polymer or very high polymer, we will penalize our model for just weight instead of penalizing the model for like the mean square difference for just getting the correct answer.
Right.
And if our weights are actually less than less than one, then it actually doesn't make as much sense because it starts to be like a smaller and smaller and smaller number,
Mm-hmm.
and it doesn't really
Yeah. Okay. So right. So it does matter whether our weights are above one or below one. Let's say our weights are on average above one, or the key ones are. Okay. So you're right. So that means in practice, it's going to penalize. It's going to care more about how big your weights are than it is going to care about um, um, how close you are to the points. Okay. But if you think about this as a prior, there's another way we can think about the exact same thing. Yeah.
Say if any single weight has a very large activation, then the model itself is very dependent on a specific weight. So in the context of dropout, you don't have a very robust, redundant neural network. That's just with regards to a neural network.
Yeah, so I don't know if you could hear online. So the comment related to like if there's one very large weight, um, uh, then that's going to contribute a lot to this penalty, and a comparison to like what's going to happen if we throw dropout in our network. Let's see here in the chat. Yeah, I guess you're constraining your weights even more.
because we usually like do some initialization on the network or some other kind of trying to our ways to be like normally distributed now very big outliers. But like in general, I do the period of like one of the versions like very big number and the autonomous will be dominated by the by that big number.
So if we follow this train of thought and we just kept upping it from 10th power to 100th power to 1000th power in the limit up to infinity, then what does our eventual model turn into? All zeros. Yes. So for linear type model, you get back to the horizontal line because you've just constrained everything. Yeah. Right. So you can see where like by adding this regularization and cranking it up, you effectively eventually, no matter what your degree polynomial is, if you crank that penalty enough, you turn it back into the degree zero polynomial. Now, I'm not saying that you're going to exactly hit all the points in between, but like in the limit, that's what's happening. What happens if we do the other thing? What happens if instead of squaring the loss term, we crank that up and we say loss to the 10th power with or without regularization? What does that do?
So that's basically like, if I reframe it as minimizing the mean squared error, which is equivalent to that, if you're giving more weight to names that have large errors, then you are going to be basically ignoring outliers.
If we increase the power, we won't be ignoring the outliers. It's the other. Yes. Yes, we're going to be emphasizing outliers even more. Okay. And so if we kept going and instead of squaring the residual, right? So we have here the residual y minus our prediction. Okay. The label y minus prediction. If instead of squaring it, we did 10th power, if we did 100th, 1000th in the limit, what are we going to get? You can't tell me exactly what the curve looks like, but can you kind of imagine what the model's going to care about in the limit as we just keep growing?
About this, but I would just maybe think that the regularization parameter would pick up all the powers, so it would just be some sort of like Gaussian or something.
Well, let's say there's no regularization. Just what happens if we just keep cranking up the powers on our error term? So you can't tell me what the shape of the curve is going to look like, but what behavior is the model going to chase? That's the case. It is going to be a form of overfitting, but what I'm trying to get at is what it's going to care about is whichever data point has the largest error. So when you take that error and you do it to the 1000th power, if that one's 100 and all the other ones are 10, the other 10s don't even matter at that point. That 100 to the 1000th power. And so all it's going to want to do is minimize the largest error, absolute error, right? And it'll keep doing it until basically by doing so, something else now becomes the newest, largest. Okay. So then basically it's just going to say, what crazy function, if you did like sort of in the limit, the infinite power, right? It's going to say, what crazy function can I find? Doesn't matter how wiggly it is or whatever, that it has all these different deviations, but the maximum deviation, I'm going to make that one as small as possible. Yeah. So in a more realistic data set, if you have a 0.1 error here and a 0.2 there and a -0.1 and a whatever, and somewhere you just have one that's a little bigger, you have a 1.5 error. Okay, it's not going to care about all those other ones. It'll do anything to ruin your other predictions just to reduce this 1.5 until it's ruined the others so much that they are now equal magnitude to what you're doing. Yes.
So we have a do model fitting for like the best price of a home. If you have a single house that's like, I don't know, $500 billion, yes, right? The model is going to pay attention to that.
Or if you had a terrible buyer or a terrible owner where the buyer totally overpaid, this one house where they paid double what they should have is going to screw up your entire model, right? Or this one owner that was just desperate. You know, there was a tragedy in the family, a divorce, a death, or whatever, and they just unloaded it for half of what it's worth. It's going to completely screw up your model. I bring up these extremes not because you're likely to run into them in practice, but I've had people ask me like, well, like why do I have to use mean squared error? Why can't I use absolute value, MAE, you know, or why can't we use something else, right? And why do we use this regularization term? I mean, in principle, you could use L4 instead of L2 or whatever. No. And there's a reason. And so that's what I'm trying to get to is that we didn't really go through, and I don't want to try to go through the math. But the squared loss gives you the exact solution, assuming that your optimizer finds the global minimum, okay? It gives you the exact solution, assuming Gaussian error around your training data. Okay, your training logs. That may not be exactly true. Okay, but whether it's due to measurement error or fluctuations in the actual phenomenon that you're measuring or whatever, that's a like pretty darn good assumption, and that's why people use this. If you used x to the fourth, or you know, the error to the fourth instead of the squared, that's assuming that you have a much more narrow peaked, that you have very little error in your measurements. And it's saying that, wait a second, I'm going to penalize deviations a lot more because I'm expecting things to be super tight to what we measured. And so if you have this one error, this little more, this 1.5, that model is going to say, that seems very unlikely to me because our measurements are super accurate. Okay. And then if you use like just absolute value, then you're basically saying a different prior that I think there's actually a lot more error possible in my measurements. And so I'm not going to penalize them. Actually, I would expect some of my points are going to be much farther from the truth than what Gaussian would indicate. Gaussian would indicate, right, 95% are going to be within two standard deviations. Right. So if you do mean absolute error, you're saying I'm not going to penalize for outliers. So again, this informs, again, I'm not coming at this from a super mathematical perspective. This informs your decision about removing outliers in your data. This informs like the loss function. And the loss function is not like, hey, we get a pretty good answer. It is exactly mathematically the peak, you know, of the curve, assuming Gaussian error around your labels. So if you do anything other than mean squared error on a regression problem, if the data is actually Gaussian distributed, you're not getting the perfect answer. You're slightly off. And so then the other thing I want to throw in is that as soon as you add regularization, you're not getting the perfect answer. Okay. So like if you're doing RL, you guys may be familiar. If you have an epsilon greedy strategy, it doesn't actually give you the optimal solution. So in a simple case where it's like you predict heads, you win, you predict tails, you lose, you should just predict heads 100% of the time. But epsilon greedy is going to say, no, only predict heads 1 minus epsilon percent of the time. Anytime you futz with this, you're not actually getting the mathematically exact solution. So that was a little bit of a whatever, a long thing, but I wanted to, Ryan, I was reading the chapter and it's very theoretical. And there was a question in Slack, and I was like, I actually, you know, honestly just did not spend the energy to go through all the formula for Gaussian, and then yeah.
It's a paper, so.
Okay, well that
was just to go through it.
Yeah. Okay.
I did.
Yeah, that might be nice to do that if we have time at the end. But, you know, I mean, the formula, we know the closed formula, whatever it is, 1/2 sigma times, you know, e to the whatever, and it's a quadratic term. And, you know, okay, so one last example. So let's say you did polynomial regression with degree 3. So you have x squared, and x cubed, okay? And you just do regular linear regression, mean squared error loss, and your x term is 0. And your x squared term is 0. So in fact, all you're doing is optimizing x cubed. Okay. Are you going to get the same answer if you do polynomial regression degree 3 in x versus if you did straight linear regression with x cubed as your input?
if you had like x cubed as the function that you're trying to guess, essentially, like the same thing as having zero error, and then optimizing just that cube regularization parameter.
So I'm not 100% sure of the answer to this, but um, it the question is, how do you model the Gaussian noise? Okay, so if you model the Gaussian noise in X, then that Gaussian noise around X is not the same thing for X cubed. But if you model the Gaussian noise as Gaussian noise after you've cubed it, then you get then you get the same answer. So I think the end result is yes, I think the noise is modeled that way. Okay. But if you do generalized linear models, okay, so logistic regression, sine regression, anything where you have a link function, now the Gaussian noise, you may want Gaussian noise in your measurement X, but what it's actually doing is Gaussian noise on your X cubed. And so now, I didn't ask the question right. But so basically what I'm saying is the answer you get is for my original question about the X cubed, the answer you get is if you model Gaussian noise around X cubed. And that's not the same answer as if you modeled Gaussian noise around X. And so I ran into this one time when I was doing a regression problem, and I was, again, applying a polynomial, applying different functions to X. And so what I found was like I had some rather large transformations of X. Okay. And so, for example, if you have X cubed and your X value is, let's say, 10. Okay. If you see Gaussian noise around X cubed, that's actually a really tiny deviation in X because you're taking the cube root of that Gaussian noise. So what I found was that when I had real Gaussian noise around X, I then cubed it, it would cause these much bigger deviations than my model was expecting. And so my model was telling me, you have a really good fit to this X cubed function. But then when I put real data through it, I was getting much larger errors than I was expecting because it was modeling the noise on X cubed. It wasn't modeling the noise on X. I said it wrong originally, but that was what I was trying to get. So anyway, I bring all of this up because this chapter is very theoretical, and I don't know that you're going to work on problems the way it's stated in the book. But I really do feel like understanding this allows you to understand what is the impact of my outliers? What is the impact of my regularization? You know, when I'm combating overfitting, what are some of the potential consequences in the terms of the suboptimality of my solution? And, you know, if you look, there are people who use L1 loss, L2 loss, and then there's what the heck is it? The one that's the blended L1 and L2.
Elastic.
No. Sorry, not the penalty. The loss function. It's like between 1 and -1. It's linear and then it's squared. Anyway, my point is people use these things because they're trying to blend how much do I penalize large deviations? How much am I going to deal with outliers or not or whatever? So, sorry, Ryan, that was a very large
No,
deviation.
it's good. It's good examples.
Yeah.
But just here, I can speak words, but do they like an L3, like regularization parameter? Does that have the potential to like add instability to it? Because I'm imagining like an x cube function or like an x whatever to the fourth function, and like there's a lot of like local minima for the cube function goes up and down, etc. Does it make it more unstable, or is that necessary for like say making it of the same scale as like a fit that might be cube or something?
I think generally speaking, the more regularization, the more penalty you add, it makes your solution. I don't know if this is a technical term that we should be using a certain way, okay? But in general, it makes it more stable in the sense that perturbations to your data points cause small changes to your model. Without regularization, perturbations to your data points can cause large changes to your model. Okay. So if you have enough penalization, you take 1 point and you wiggle it a lot by a factor of 100, and your model doesn't even change. Right? It moves one tiny, tiny bit. Without that, right? You have squared loss. You multiply by 100, and then that point has shifted your entire model. So it makes it more stable, and if you crank it up enough, it makes it stable to the point of pathologically pursuing stability over following your data.
Doesn't make it like less reliable if like say like the polynomial function of the regularization parameter has like a lot of minimum to it. If it's wiggle, like that doesn't really matter as much.
In the extreme, like what I was saying, you do something crazy, 100th power, blah, 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 yeah, then it's going to actually prevent you from being able to be expressive. Okay. But in general, the more the bigger your lambda and the no, I don't think anybody actually uses more than L2 penalty. But if you did, if you use the absolute value of L3 or you used L4, whatever, it would have the effect of saying, like, I really, really, really expect small parameters. And I don't care what your data is. You just can't have big parameters. Sorry, John. Which I think, ultimately is probably bad. But so that's where ultimately we can get into this, and we can look into section 3 when we talk about actually doing like Bayesian inference. Ultimately, you have to think about what does your data look like. And this whole idea of having small parameters, and generalization, I think it's generally true, but it is based on the assumption that your curve, your Y that you're trying to model is sort of continuous and smooth, right? So if you look at the example they had in there, which was just, you see sort of roughly one period of a sine curve, okay? Well, what if actually it was that plus some other function that instead of having a period of 10, had a period of like 10 to the minus 4. And it's 4 orders of magnitude doing this, but we just don't see it because we only have 10 data points, right? It's impossible for you to pick that up, with this. And so ultimately, it goes back to that whole question of like, know your data, right? So you have to say like, yeah, in this case, it's like kind of intuitive, but we look at the points and we just assume that if you drew a roughly straight line between each of the data points, that's going to roughly interpolate accurate values. But if what's really going on is there's some trig function with a period that's 1e minus 4, then that's a ridiculous assumption. That's a totally, now you also can't model that with 10 data points. Okay. But nevertheless, there's no reason to assume that this would generalize well, right? It may be the best you can do, but there's no reason to assume it generalize well. So it's those priors around our data that lead us to our priors around our parameters.
Minus 2, that comes from assuming a Gaussian 90, you get a 95%. Trying to count for 95% of.
Yeah, so it's a way of interpreting, right? A squared with a lambda of, I guess, 1 is saying that we expect 95% of our parameters to be between 2 and -2, and we're going to sort of penalize if more and more the farther you get from
But, I didn't know that there wasn't, how do you know you have, how do you know the narrowness of your Gaussian peak? How do you know it's not,
Yeah, no, that's a great question, and I honestly can't answer it for the life of me. We have this thing where smooth data, we tend to have large parameters, but I'd have to read a whole bunch of research parameters, and I don't even know if people really truly deeply know why small parameters work. It's empirically, it's very easy to see that if you have 10 data points and they kind of look like this, and the magnitude of your largest data point is whatever it is on here, you know, +2, -2, right? That having parameters that are an order of magnitude larger than that just feels wrong, right? All your values are, between 2 and -2. Why would you have a parameter of +100 here and -100 there that like largely cancel each other out, but they leave this little funny residual that gets you just a little bit closer to that one data point that you're having trouble fitting, you know? So intuitively makes sense to me, but I can't speak to theory any deeper. All right, thanks, Ryan.
Yeah, yeah. I pulled up, so just on the practical side of things, most people will, if you are doing this kind of modeling, if you're doing linear regression or the polynomial regression or anything that we've mentioned, most people will go to scikit-learn. I feel like it has become a little bit less popular because now everyone just does deep learning, gradient boosting, all of that stuff. But there was a point where scikit-learn I felt like was like the core, most important library a data scientist could know. Um, so just to point out, there's a few different variants of this. So like they have the base linear regression. This is what we've been talking about. This is no regularization, no priors or anything. It's just do linear regression. And they have all of these other flavors along in here. So this one thing to mention is this linear regression is doing that closed form solving that we were talking about. It will just directly say like this is the outcome. Um, but in certain cases it can actually be very slow. I don't remember exactly if it's a lot of features or a lot of rows or what it was, but this can be like prohibitively slow depending on the characteristics. And so what I ended up using often was this SGD regressor. And this is basically saying, okay, let's do this sort of optimization thing that SGD that we've discussed in some of the past chapters and just take little steps, say get closer, 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 and then once you reach some like closeness factor, you just say good enough and you just end. So it's not using the closed form solution necessarily. It's just saying take steps in the direction of the gradient. And then you'll get some final value that's close enough to the good answer. But it also includes the sort of regularization that we were talking about. So you can do L2, L1, elastic net. I think you might be able to just define your own like P norm, like Ted was saying, you could set it to 1,000, I think somehow. I'm not exactly positive, but just throwing kind of the practical, like if you're trying to do this, there's libraries that exist. You don't have to go review all the math and figure out all of the details of this. Um, so going back to the slides, um, we talked about the two different methods, and so now looking at Bayesian linear regression, it's similar in the model, so we're using the same kind of architecture, but now we're injecting a prior, like in the MAP case, But in this, what we're trying to do, we're not trying to find the optimal parameters. We're basically saying we have this prior, it tells us what the parameters should generally look like. And then we're going to do predictions that kind of shows all possible outcomes and their probabilities. So on the left, what we have here is our training set. So we have all of these marks that represent our input X's and our output Y's. And then we see the fit that's represented by the different methods that we've talked about. So we have MLE, MAP, and then this is the Bayesian linear regression. And so what we can see is that the Bayesian is giving us this sort of uncertainty estimate. So we have this sort of darker inner portion. I think they're trying to show like this is one standard deviation up and down from the mean, and this is two. And so the slightly lighter gray is showing the regions of uncertainty and the amount of spread that we would expect. So you can see there's a region like here where it's pretty certain, like we know that it's probably going to be plus or minus maybe only zero point 0.1 or zero point 0.2. But then we have certain regions where we don't have much data where it just kind of expands out and it says it could be -4, it could be +4. I have no idea. There's plenty of possible outcomes. And so this can kind of inform you of the areas that you don't have enough data for, you probably shouldn't be using the model at all, or at least like have some uncertainty in these regions. You basically say this is unexplored. I can't make a confident prediction in this region. So that's a very valuable thing to have. And so these red lines are showing like here's kind of many of the different possibilities that could come out of the Bayesian output. So saying here's many different sets of parameters that you could use, and here's the different outcomes that they would simulate. Um, so here's some more examples of this. This is going back to like we were looking at increasing the polynomials. So at low count, so having only three, we can see okay, here's the various different methods. It's pretty confident. There's not much spread. But if we do 5 plus, then we end up getting way more spread, way more variation. We say, okay, we have a very high degree polynomial. It could be many different things that make this pass through the data points that we have, and we can't reasonably extrapolate in between them. Um, so the kind of interesting thing here is you're seeing much higher uncertainty here, but you have the same exact amount of data. So just because you see less uncertainty here doesn't necessarily guarantee that it's going to be more accurate just because there's less variation. But it is telling you something about like this is not a well fit model. If you say my average value is 0, my max is 2, my minimum is -2, and you see that the models make predictions of 100, then you probably know that it's not a reliable model that you really want to um, use for anything important. You need to find more data, or you need to reduce the polynomial, or something else to make it probably give more reliable predictions. Um, so wrapping up all of the stuff that we've looked at. So we looked at maximum likelihood. So that's a point estimate of the parameters that maximize the likelihood of y given x. So there's no prior in that case. It's just saying unconstrained. Uh, find the set of weights that will make the most likely y. So adjust the slope, do whatever you need for the polynomials. It's just basically full range, do whatever you can to kind of match the distribution at all points. And then we had MAP, and that was introducing a prior. So that constrains the parameters in some way. You can add regularization. You can say, I think that the weights are going to be um, -2 +2, you have some Gaussian prior or something like that. In practice, I haven't seen that often, but I think depending on the realm that you live in, maybe it's um, more common. I just haven't really had a scenario where I really have much prior for what the parameters are going to look like. Um, one of the powerful things that we talked about is like these linear models don't necessarily have to represent linear functions. They can also do nonlinear. You can do polynomial or some other transform that allows you to do regression of even more complicated representations. Um, and then we looked at the Bayesian linear models, and that one you're not really caring about the parameters. You're caring about the distribution of the outputs based on what reasonable parameters could be. So you're kind of sweeping through all of the possibilities and saying what does the reasonable outcomes look like. Um, and I think that's all I have for today. Um, thank you, everyone. Any questions?
That's awesome. Thanks, Ryan. And so, one quick thing is if Bayesian linear models basically give you the same point solution if you look at the mean of the Bayesian predictions, but they also give you um, this this great idea about uncertainty and not just uncertainty overall, but uncertainty for any given input value. Well, then why don't we just always use that instead of maximum likelihood, right? So the answer is because unfortunately Bayesian is really hard and complicated and expensive, and so um, yeah, it'd be nice if we could, but
The building the model, we're learning the distribution of the data. With more data in, the model be able to say, oh, well, this is narrowly, very narrowly distributed around, you know, certain value.
that's an interesting question. I don't know. So the question, I don't know if you guys could hear, is like, is there a way you can kind of have the model learn, like, oh, here the data is very narrowly distributed. Here, maybe it's wider. Off the top of my head, I'm not familiar. I'm guessing somebody's probably tried to do that, and of course, lots of people have tried to figure out is there. So in this, they showed that for a linear model, Bayesian is tractable. Okay, so is there a form of model that has even more expressivity, but is still tractable? And so then, you know, I know that there's like, they didn't really explain it, but they showed like the graphical models a couple places in the chapter, right? And so there's things you can do with graphical models to decompose things into smaller components, and then that makes the problem, more. But ultimately, it gets super expensive. So I don't uh, overly simplistically, I don't think anybody has really been that successful, or otherwise it would take over because you're going to get more information. Uh, One of the coolest things that I heard of, which I I don't know if I'm getting the name right. I think is it Monte Carlo Dropout? Is that the name of it, Ryan? But um, basically, people said we have dropout that we use for regularization, but when you're doing inference, of course, you turn it off, right? Because it's going to give you more variability in your answers. Uh, Somebody figured out an interesting thing you can do is you turn on dropout while you're doing inference and you repeat predictions and you'll get a spread of responses because of the different dropouts. Nobody's saying that we have a mathematical uh, 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 definition of what you'll get, okay? But you will notice that for certain predictions, you'll get a much tighter spread of things. And in others, you'll get a much wider spread. And so then this Monte Carlo dropout acts a little bit like telling you that standard deviation, that variation that you get from the Bayesian model. Um, I thought that was like super interesting. I don't know how many people use it. I don't know if there's other techniques people have found, but trying to give some sense of the uncertainty. And then Ryan, I think you said something really great, which is that when you looked at that top diagram on that one slide, just because the model is certain doesn't mean the model's right. Okay, so you should not mistake model certainty for like real world certainty,
Yeah, yeah.
right? That's just the model telling you within my expressive power, I had a wide range of possibilities that I could have predicted here, so I'm quite uncertain, right? That's just relative to its expressive power, not relative to the truth. Any other questions, guys?
So machine learning practitioners, they developed linear regression, but obviously linear regression's been around much longer and a lot of different fields and domains use it. I've never really seen a conversation between traditional statisticians and machine learning practitioners about statistical significance of the coefficients. Do you have any comment on that?
I answer this question because I was working on linear model for statistical inference. And I would say you use two different languages and two different packages, because if you want to just make a model for predicting future events, you use scikit-learn. If you want to do some statistical inference and statistical model, then you switch to R language and you use GLM or GLMNet package for that. And you add for the model some potential covariance that you might see. And then as an output, you will get a p-value for the model, and you will see if this particular coefficient is statistically significant for model or not. So yeah, it's basically two different approaches and two different problems, and people sometimes mix them up, but and I think it's a great question.
Yeah, so there's there's like a related phenomenon of when you build a model that makes predictions, do you just care that the model is right, or do you want to understand why? Right? And so more recently, we've seen even more monetization of the I don't care why, just as long as it's right. Okay. So if you build a recommender and somebody goes to your site and they buy a t-shirt and you say, would you also like to buy this other thing? And if you increase sales 10%, nobody cares why that recommendation was better than another recommendation. They just take the 10% money and move them, Whereas like if you're doing medical diagnoses or something, like people care, why you made that diagnosis instead of different one or whatever, right? So there's been a lot, I think, lately. I think about this was around 20 years ago. Leo Bryman, I think that's how you pronounce his last name, but he's the father of random forest. So before we even had XGBoost, and he had a very famous paper. I'm trying to remember the two. What was it? Ryan, you don't remember the title of this one, do you?
No, I don't.
It's the two something, and I'm going to get it wrong. I'm going to say the two worlds, but it's not worlds, okay? But basically, he was talking about parametric and non-parametric models, okay? And so random forest, which he invented, is non-parametric, and you can't get any kind of statistical significance or anything out of it. You just get better predictions than if you, generally speaking, use linear regression, right? And so all the, whatever decades, centuries of probabilistic learning, and so there was a lot of headbutting, and I think that's still true a couple decades later, but at the end of the day, it's like there are use cases where like you have a website and you're selling things where you just have empirical confirmation, right? And so much of the world. So like AlphaFold predicts a 3D protein shape. Well, now they do even more, but the original one, right? It was just proteins. And so it's like if we can get a really, really accurate model, then we can kind of confirm that hey, this has this shape, and so it should bind very tightly in this particular location, and we can just kind of confirm that rather than saying I need some kind of standard deviations to tell me whether or not this 3D prediction is correct. So I think that yeah, um, a lot of people have really just leaned heavily into, where we can just use the model and where we can empirically, see how its predictions work rather than, um, but if you're in certain industries like financial, approving loans or whatever, then you are more constrained in terms of being, regulation requiring explanations, and probably you care more about like having, maybe like if you were trying to do something for insurance, like now this is no longer about the mean. You need to know like your risk. What are the odds that if I have this life insurance policy that I'm gonna have double the number of payouts that I expected? What are the odds that I have quadruple the number of payouts that I expected? What are the odds, right? You kind of want to know all that. You don't want to just know the mean.
There is some uncertainty in like when different colors, which correspond to how a model is certain about some region of the protein, and which actually corresponds to like biological science, because everything like if you want, I can say like just introduction. The proteins have polypeptide chain. The second is that have either alpha fold or beta sheets or some unstructured regions. And if you model the protein with alpha fold, you will see that the lowest uncertainty is in these unstructured regions, which is just some like polypeptide chains, some I don't know, messy object, and the highest confidence is in alpha folds or beta sheet. Yeah, so it actually has a good correspondence with like biological knowledge. Uncertainty estimation.
That's cool. And do you know where the uncertainty estimation comes from? Do they directly have a prediction head for that, or?
I think I mean, I don't know, but I think they do have some mathematical uncertainty explanation.
Yeah. Cool. Thanks. Any other questions before we wrap up? All right. Thanks everyone for joining. Ryan, thanks for presenting even though you're out of town. Really appreciate it.
Yeah, thank you, everyone.